Thanks for joining us here with Pure on Storage Field Day. I want to talk a little bit about what we've been up to with FlashBlade. And the way we thought about this is, as I shared earlier, we're going to talk a little bit about a year of FlashBlade, where we've been, what we've been up to, what we've seen. It's going to be pretty quick. And then I'm going to hand it to Rob. He's going to talk about what happens beyond 15 blades. And we're going to talk about native objects and object interfaces. And we're going to end the day or the session with looking forward. What's beyond the horizon? What's beyond the obvious? So with that, let's get started. So first, some engineering humor. This was our code name for our product when we launched for you. We call it our wedding cake because we built a white box, and I've never seen a white box before. And so the engineers got to name it, and yeah, we came out with our wedding cake. We thought it was really funny. I don't think we ever told that to anyone outside of engineering, so now it's all out there. We have lots and lots of code names. Some of them are really funny, at least to me. Since we launched, we've been involved in a whole bunch of really, really cool workloads, and we kind of hinted a lot of them. We've been installed in one of the biggest, if not the biggest, AI supercomputers. It's stuff that everyone uses. It's a really well-known brand. No, I'm not allowed to tell you who it is, but it's everywhere. We've been installed in race cars. We kind of talked a little bit about that last year, but basically simulating airflows, trying to make the system go faster, which we've also been involved in other forms of transportation, including shipping things into space. And that's pretty darn cool when you sit and you see the call home data, and you see the launch counter go down, and you see the simulations for airflow and guidance systems taking place, and it's the kind of stuff that an engineer dreams about. And we've also been installed in the world's largest databases, particularly for the web companies, and mainly aimed at doing really fast database restores from failure. These are companies who use the bandwidth essentially to recover from mishaps. Rarely the big mega outages that people see, usually functional systems, smaller systems, rack scale systems. But when you have thousands of racks, it becomes pretty big quickly. So that's a little bit of the background and kind of where we've been. We rarely talk about sort of the super simple use cases like home directories in VMware and things like that, but yeah, we're installing those too. So we also made the product better over the last year. When we came out at launch last year, when I spoke to you, we told you 500,000 IOPS, but we only actually seen 200,000. That's all we had seen. Between that moment in time and we actually started shipping is when we got 500,000. We had a line of sight of 500,000. We had not observed it yet. But we made a staking ground and said that's going to be our goal. And then we hit 500,000 IOPS. We did hit the bandwidth, 15 gig a second. That we hit, but IOPS requires quite a bit of work. Since then, we kept on improving the system. So I'll tell you what we've done over the last year. In October, 3 months after, we hit 1.2 million IOPS. Again, it's just software, you make it better. And so right around the end of the year, we hit 1.5 million IOPS. And this is not benchmarking numbers. This is what customer reported to us. This is what we see in the call home logs. I mean, it's pretty outstanding. We made it 3 times faster in essentially the first 6 months. And that's what you should expect from a system like this. The software, we keep on improving, and making it better over time. We shipped GA, what we call our 2.0 release. We shipped it here a few months ago, about 5 months ago. And right now, we are busy adding protocols and features and capabilities to it. Some of those are obvious, things like snapshots, SMB CIFs, things like that. But some are non-obvious, and we're going to spend most, if not all of our time here talking about the things that are not obvious. Because I don't think you should spend a lot of time with obvious stuff. Snapshot ship is in beta right now, ships this quarter. So, with that, I'm done. I had the easy part here. Now we're going to go deep. Over to Rob.
Cool. So as Par mentioned, we've been consistently growing performance in the system over the last year. What I want to use this next section is really talking about how we're going to make that next large jump forward. And so what we're really talking about is the next step along the path of making FlashBlade even bigger and faster than it is today. And as we do that, we really want to focus on 3 main areas, 3 main kind of goals that we want to set out to achieve. The first being linear kind of scale in capacity, right? We want to start talking about systems that start as small as a couple dozen terabytes, but really start pushing into systems in the size ranges of several dozen petabytes. Right? We want to do that all non-disruptively, all very elastically. We also want to be talking about linearly scaling our performance, right? So we want to be growing as we're adding blades in the system, keep that keep that scale and performance that we have today from 7 to 15 blades. We want to keep extending that out as we add more and more blades beyond the 15 that fit in the single chassis form factor that we have today. And as we increase our capacities and we increase our performance, what we don't want to increase is complexity, right? We don't want to increase the amount of management, the amount of complexity in the system. We want to maintain the same level of simplicity of management and ease of use that we have today. And so as we look at scaling this FlashBlade system beyond the 15 blades that fit in that single chassis out to multiple chassis, or what we've in the past referred to as multi-chassis configuration, you end up with a system that physically probably looks something like this, right? We take that same 4U chassis form factor we have today that holds 15 blades. We stack a bunch of those together. We add a little bit of networking hardware, which we'll get into, to interconnect them. And so from a physical point of view, this is roughly what the system will end up looking like. But as we start peeling back the layers and start looking at how is this actually implemented? How do we actually achieve those goals of linear capacity scale, linear performance scale? The system actually starts looking a lot more like this. It starts looking a lot more like kind of a magical chassis that just contains an ever-growing number of blades. And what I mean by that is, as we dive into the kind of three main layers of the system that I want to talk about today, the networking fabric, how we distribute processing, control processing in the system, and how we distribute data and place data within the system, what you'll see is that the majority of the software within the system really views this configuration as just a large collection of blades, right? Frankly, the fact that this is split over multiple chassis and so on and so forth is really just a limitation of, well, needing to rack and stack this in actual data centers, right? The software itself really views the system as growing out one blade at a time. Beyond, there's nothing magical about 15 other than that's just what happens to fit in the chassis form factor. And so the three main areas that I want to dive into today are really looking at, as we scale beyond those first 15 blades, how does the networking fabric, how do we add more, how do we add more bandwidth, how do we add more connectivity to the system to allow these blades to intercommunicate with one another? How do we scale that networking fabric? The second area I want to dive into is how do we move processing? How do we move control processing around in the system? How do we achieve that linear scale and performance build out as we add blades? And the third area is, as we add blades to the system and grow it larger and larger, how does the system behave in terms of data placement, right? When you're talking about 75 blades, how are we thinking about placing data within the system? All right. So before we dive into the details of those three areas, I just want to do a little bit of a recap, high-level overview of the architecture of FlashBlade, because it's a little bit different than, it's quite a bit different than a lot of other systems out there. And so at a high level, we think of FlashBlade architecture as really three levels, right? Kind of at the top level, we're looking at integrated networking. We're looking at how do we manage the networking connections within the system. And if you remember from last year's presentation, one of the distinguishing characteristics of FlashBlade is that we didn't stop at the store, at kind of the water's edge of storage, right? We recognized that in order to create management simplicity around scale-out storage, we really needed to integrate the networking, integrate the management of the networking into the system. And so in the networking tier, what we've done, if you recall, is we've integrated physical networking switch parts, switch chips, into the single chassis form factor you have today. That's what's in the fabric module. But more importantly than the hardware, what we've done is we've programmed those switch chips with essentially software-defined networking logic that programs those switches to really behave in two different ways, right? Those switches, those fabric modules, are being put to work to manage essentially two different networks, right? Historically, you've had an external network for client connections, and you've had an internal network, some sort of backplane fabric that allows the nodes or the blades within the system to talk with one another. What we've done is we've flattened those two networks electrically into one and really managed those virtually through software programming. And so really at the fabric module layer, what we've done is we've integrated those two networks and managed that through software. What we're doing for the external network is really asking that switch chip, programming the switch chip to behave as a load balancer for connections coming into the system. And for the internal network, we're asking the switch to essentially behave as a core switch, basically core switching functionality for traffic between the blades. diving a layer deeper, one of the other kind of distinguishing characteristics of the FlashBlade architecture is that we've really moved away from the kind of more traditional single controller drive shelf type architecture. We don't have any discrete controller tier in the system. What we've done instead is distributed the control logic within the system across each of the blades. This is a truly distributed, shared nothing, scale-out system, so that as we add blades into the system, those additional CPU cores, DRAM, the compute capacity that comes with each blade is really put to use. And as a bit of a recap, the way that we've done that is, at a high level, we basically take a look at all the logic that typically runs in a storage controller, right? To manage data placement, namespace rules, data recovery, data movements, I/O scheduling, all of that logic, right? What we've done is we've taken a look at taking that big bundle of logic and essentially breaking it up into separable, partitionable, autonomous pieces that can be run in parallel. In some ways, you can almost think of it as we took a storage controller software and we've essentially sliced it into pieces and virtualized it, and really built a system around a collection of these mini storage controllers, if you will, mini virtual controllers. And what we can do then is, if we treat these almost like VMs, or think of it mentally almost as VMs, what we can do is, as we add resources into the system, as we add more blades into the system that are providing more CPU and more DRAM, we can then take parts of the control logic and move them around in the system to load balance, right? And so that's essentially at a high level how we achieve scale, how we achieve a growth in performance in the system as we keep adding hardware.
Rob,
yes.
So as you build us out, is there an incremental extra overhead per blade because of the communication that should go between?
Right. So that's a good question. I'll repeat it just for the audio. So the question from Chris is, as we build this out, is there any incremental overhead that comes from managing these partitions on each blade? And so that's a really good question. It turns out that we've put a lot of work into the software, a lot of really a lot of focus in the software and how we've written the software to dramatically minimize that. And what you can see by that is, we ship today 8 terabyte blades and 52 terabyte blades, and they're essentially shipping on basically the same processors, right? What that means is that our ability to do that means that the control logic we run, right, is really not a function of the storage capacity that's managed, right? It's really a function of directly proportionate to the amount of client traffic and client load that's coming into the system. And as far as managing these partitions within the system, it's extremely light, right? So basically, these partitions, other than coordinating distributed transactions or coordinating operations like renaming a file from one directory to another, these partitions largely don't interact with one another, right? That's a property we specifically wanted to have in order to maintain kind of parallelism and concurrency without creating contention in the system.
Yeah. So to follow on from that, is the way that you're doing that analogous to a virtualized environment like VMware and having different virtual machines running in a hypervisor environment, or is it more like a container environment where you have something like a Kubernetes style of orchestration of independent processes?
Right. So the way that we move these partitions around, I use the analogy of, you can almost think of it like a virtual controller, you can almost think of it like a VM. In reality, these are just software constructs within our own process, right? And so what we've done is we've layered the software, we've layered the design of the software so that the control logic that's running in this tier is largely stateless, right? And so what we can do is, within our software, we can basically say, look, the software process running on this blade at this point in time is responsible for this many parts of the control, this many partitions, but if the system as a whole decides that it's advantageous to load balance that and move it elsewhere, it can go ahead and do that. And essentially, through our own software constructs, and it's a bit more analogous to containers, through our own software constructs, essentially, clean up a bunch of data structures and without having to start a new process or kill processes or anything like that. Cool. All right, and so really the takeaway point, from this layer in terms of how we distribute control in the system is that this distributed kind of control scheme allows us to linearly scale performance by creating parallelism and kind of independence between these partitions, each of these partitions, in terms of how they manage data, are acting independently. Each of these partitions can essentially work with the entire storage capacity of the system across the blades. To put that, to make a concrete example out of that, what that means is that as one of these partitions needs to place data within the system, it needs to form, for example, a RAID stripe or place data into NVRAM, it has direct ability to write to flash on each of the other blades, right? So that's really where a lot of the backplane kind of internal network traffic is happening, is individual portions of that control logic writing to the storage tier. Right? And again, the storage tier is distributed across each of the blades. Each of the blades is providing both NVRAM resources and flash resources. Right? We use the NVRAM to stage kind of those high-frequency transactional updates. And then as NVRAM kind of fills up and data lives in the system a bit longer, we'll flush those out to flash in very much the same way that a more traditional storage controller would work with a drive shelf. As we flush that out to flash, we'll write it into more kind of efficient RAID structures, N+2 erasure coded.
Does a partition correspond to some segment of a directory, or is it independent of directory structure, or?
Great. So the question is, does a partition correspond to some portion of the directory, or how does it correspond to the directory structure? It's a really good question. So the way that we break up the namespace, right, a file system namespace, for example, we put particular care not to break that namespace up along directory boundaries or directory tree boundaries. And the reason for that is a lot of our workloads, a lot of our customer workloads, vary quite a bit in terms of I/O patterns and how they work with files. Some applications work with a small number of files in a directory. There are other applications that might work with tens of millions of files in a directory. And so it's really important when we break up that namespace and break up those directories across these partitions that we create as much load balancing and randomization as we can. And so what we do is we actually take things like large directories or large files, and we actually break those up and split the management of those pieces of the namespace, whether it's a large file or a large directory. We'll actually split that up and push it into multiple different partitions.
So there's no intention to try to keep a directory within one partition or anything like that?
Correct. In fact,
it's the opposite.
In fact, there's the opposite. There's no, yeah, exactly.
All right, so just to dive a little bit deeper into data distribution, I mentioned before that as each of the parts of the control logic, one of those control partitions wants to place data into flash, what it's going to do is write to flash on each of the blades, right? Or it's going to place the data across the, it's going to find places across the entire set of blades to place that data. And so as an example, as we want to form RAID stripes, those RAID stripes are going to cross blades, not necessarily placing data on every blade, but the point is that each blade's capacity of flash and NVRAM is available to each part of the control logic. And just as a quick reminder, we've got the blades providing both NVRAM and flash. We triplicate those updates to NVRAM, and longer-term data goes to flash in those kind of more efficiently encoded RAID stripes. Yes?
You said they're all acting independently.
Yes.
If they're acting independently, how do they communicate with each other to say what capacity they have, how they start to run down, how you load balance the capacity each node has compared to the others? How do you sort of make sure that you're not biasing one node or another in terms of capacity or performance?
Okay. So each of these partitions is acting independently for decisions like enforcing namespace rules, which write landed first, who created the file in this directory, how are we writing data to flash, and how do we locate what part of flash to write into. There is a higher level of control that coordinates across the partitions to determine things like, which blades have idle resources, where partitions should run, so on and so forth. If you add a blade or remove a blade, there's some layer of control and kind of orchestration logic that's very, very light, but it exists to essentially determine how partitions should, be moved around each other. But the important point is that layer of control, that logic, exists completely outside of the data path. All right, so now that we've kind of done a bit of a refresher kind of view of the high-level architecture, I want to dive into how the networking fabric, how that networking layer grows to expand as we scale the system beyond those 15 blades, as we scale the system beyond that single first chassis. And so, I mentioned before, this is kind of, Par mentioned the rudimentary slides that engineering has produced here. So I mentioned before that the Fabric module at a high level is performing two major functions for kind of network management. In terms of managing that external network, what we've really done is program that to serve as a load balancer, and for that internal network, we're essentially doing core switching. And so as we scale beyond that single first chassis and we add more chassis together, the first thing that becomes apparent is, well, we need some layer of hardware, we need some mechanism to connect these chassis together, to interconnect them. And so what we've done is just like we've developed an integrated Fabric module that resides within the chassis, what we're doing as we scale beyond that first chassis is we're adding an external Fabric module, right? And so again, in kind of much the same way that there isn't really that much magic happening in the hardware for the Fabric module, it's really all in software, we really take that same philosophy as we push out and add that external Fabric module. All we've really done is moved around some of the logic in the system, right? Some of the logic that used to reside within that chassis to manage that external network's load balancing, we've essentially just moved that software logic to now program the external Fabric module and push a lot of that load balancing logic essentially to that upper tier. Right? For the internal network switching logic, we've essentially now split that up, right? What we can do is we can still manage the switching logic for intra-chassis communication, essentially communication between blades that stays within that single chassis. We can still manage that at the chassis Fabric module layer. What we're doing now is kind of splitting that internal network management up so that inter-chassis traffic, right? Traffic between blades that has to cross chassis boundaries is now pushed up to that external Fabric module. But really the takeaway point here is just like we view the hardware integration of the Fabric module today that sits within that chassis as nothing special other than a place to run software, as we push out and add that external Fabric module, we really have that same philosophy. It's just a matter of figuring out where in the system we want to put the software logic.
Is that external Fabric module a rack mount switch?
Yes, so the external Fabric module is a rack-mounted switch. Yeah. But the important point is it's part of the surface area of the product, right? It's something that is a pure product. It's managed by us. It's managed through our UI and everything.
It is the external Fabric module one switch or two?
So it's two for redundancy, just like the Fabric modules. Just like the Fabric module layer here is actually two physical units.
And what's the overhead of going back in through?
So the question from Chris is, what's the overhead of going back through that? I'm actually going to get to that in the next slide. So.
Yeah, so that external Fabric switch that you're using, so you're saying that's a pure product. Now, you're not really a networking company, so I'm assuming that's some kind of white box thing that you run pure software on, but the physical hardware is switch manufactured, like it'd be a Broadcom Trident 3 or something similar.
Right. So the way to think about it is just like the Fabric module we've integrated into the chassis. At the end of the day, everybody uses the same switch chips, right? So there's nothing. We're not inventing switch chips. We're not building switch chips. What we've really done is, again, taken that same philosophy of integrating the hardware with the software inside the chassis, and as we push out to the external one, we're kind of taking that same philosophy.
More similar to something like FlashStack, where you've got a partnership with Cisco for doing the switching, but in this case, you're buying the switch stuff directly. It's white box switching with pure-based software that you run on the switching fabric.
That's correct.
Yep. Okay.
And it's 4 by 40 gig up?
So we'll get to that in the next slide. Yep. So. In fact, we'll get to it now. So the switch chip that we've chosen for the external Fabric module, it's actually a 32 port 100 gigabit switch chip. And so we actually are pushing, so I mentioned before there's physically two of these units. Out of each of them, 800 gig ports pushing up. So in aggregate, it's 1.6 terabits a second. Again, that same simplicity kind of in terms of the network interface that we present today out of the single chassis, we'll push that into the external Fabric module as well. So all of those 16 ports, you would essentially gang those together as a giant port channel up into the core network.
Can one of these, you mentioned before, within a chassis, it could write to any flash or any NVRAM from any compute engine. Can that happen across this switch as well? And this is using RDMA logic, or how is it actually doing the writes? Using Ethernet, apparently?
Right. Electrically speaking, it's Ethernet. Today we use an internal kind of communication protocol based on user space networking. RDMA is in our future, and you'll see that introduced in future generation blades.
So, any of these compute modules can write to any storage in the system. Is that what you're saying?
Yes.
And so as we look at the bandwidth within the system, right, the kind of the total bandwidth of the network fabric as a whole.
Trying to do some sort of load balancing across the chassis as well as across within the storage within the chassis. I mean, so how do you determine where to actually write a byte of data, for instance?
Okay, so if you'll permit me a couple minutes, I'll get to the data placement side of things. As far as load balancing, we really think about load balancing kind of in two different tiers. One is control load balancing, how do we load balance to achieve performance, and then capacity load balancing, how do we load balance to achieve kind of even distribution of data, as well as optimal usage of the total storage capacity we have in the system. And if you'll give me a couple minutes, I'll get to the data placement part of this. And so if we look at, turning our attention back to the networking bandwidth, if we look at the network fabric as a whole, we really have two types of traffic in the system. North-south traffic, which is, really represents traffic that is originating from external clients in and out of the system. So this is, the kind of the core data path, right? I/O requests and responses coming in, reads and writes coming in and out of the system. So by pushing 800 gig ports up, in aggregate over 2 fabric modules here, we've got 1.6 terabits a second north-south. East-west, right, so this is really getting more to how do we move data around within the system. Our east-west traffic, you can kind of think about it or break it up into two different layers. We've got the east-west traffic that's constrained to the chassis, and then that which crosses chassis boundaries. For the traffic that remains within the chassis, we have the same amount of bandwidth in a multi-chassis configuration as we do in a single chassis configuration. Nothing really changes there, right? So we've got 300 gigabit a second aggregate east-west bandwidth within that chassis, and then across chassis, right? So this is inter-chassis traffic. We've got up to 1.6 terabit a second. And so really the takeaway point here is that just like in our single chassis configuration, how we've over-provisioned the amount of networking bandwidth that's available to us in that fabric module that's integrated into that single chassis, as we push out to multiple chassis configurations, we've done the same thing and really over-provisioned the amount of bandwidth that's available to us for inter-chassis communication.
So that would imply like a maximum of 6 chassis within an external fabric module, something like that.
Yeah, and so Ray's question is, so this means you can put kind of a maximum of about 6 chassis behind this external fabric module. And that's correct, given the numbers that I'm showing you right now. The takeaway point there, though, is that the numbers I'm showing you right now are based on the particular switch chip that we've chosen for our initial launch of the multi-chassis or kind of blade scale GA product. That chip is a 32-port, 100 gigabit switch chip. That chip selection is really the only thing that limits us to 5 or 6 chassis worth, right? Everything else in the system, besides this, kind of bandwidth allocation, everything else in the system treats all the blades that are within that system as kind of equals, right? And so really the only thing that's between us and scaling beyond the 5 or 6 chassis that we're going to introduce at launch is newer switch technology or kind of switch chips with more ports on them. Yes.
So in terms of the bandwidth compared to IOPS and throughput, what feedback have you had from customers in terms of how much of that networking they're using?
Sorry, the last...
How much feedback have you had from customer data to show how much of that networking they're using relative to the traffic they've got? I'm just interested to see what level of scalability it means that you've got built into there going forward.
Yeah, so that's a really good question. In terms, I'm showing you kind of top-end limits of the switching hardware that we have in place today. The question is, based on our existing customers, what kind of feedback have we gotten from actual workloads in terms of the bandwidth utilization? And so at a high level, save for 1, 2, kind of 2 or 3 customers, we haven't had customers that have really been able to max out the bandwidth even within a single chassis configuration. So today we push up, I think it's 320 gigabit a second aggregate out of a single chassis. I don't know of any customers actually that have been able to max that out.
I know the max number is about 18 gigabytes.
Okay, so the max number in the real world that we've seen is 18 gigabytes a second, and that's from an oil and gas company that's pushing into their essentially ground sonar data simulation application.
So I've got a question as far as how the math works out. If I've got 32 ports times 2, which is actually only 32 because based upon the number of chassis I have, how am I getting 1.6 terabytes east to west if I'm maxing out a connection upload, but also having 5 or 6 chassis connected?
So the math works out by putting 4. Let me see. So out of the 32 ports, we've got 4 for an ISL, we've got 8 going up, and we've got 4 ports going to each chassis. So you've got out of
That accounts for 400 or 800, depending upon the way we're looking at it, but it does not account for 1.6. That's the part I'm trying to rationalize.
So the 1.6 comes from 320 gig aggregate coming out of each chassis, because those numbers that I just gave you were for one fabric module. We've got 2, right? So you double them up, and then you've got 1.6. So cool. All right. So if we take a look at the second area I wanted to dive into is how we scale performance within the system. This really comes down to how do we manage control placement as we add those blades. And so if we take a look at how does the system work today, even within a single chassis, if we've got the single chassis at equilibrium, we've got a bunch of blades, they're running, they've got their partitions in place. As we add a new blade into the system, what happens is that orchestration layer sees pretty quickly that we've got idle resources within the system. The system kind of reaches a consensus to move some of these partitions into place, load balance everything out, everything runs a little bit faster. So this is how everything works today. This is how we scale from 7 to 15 blades within a single chassis. As we push beyond 15 blades, nothing actually changes, right? The takeaway point here is that all of the partition load balancing, all the partition movement logic, it's all done on a per blade basis. There's nothing that's constrained to a single chassis, right? And so
I'm confused, because the slide says no data movement, but the animation moved data.
Sorry, the animation here is showing control partitions. They're stateless, right? So this is the portion of the control logic.
That's metadata ownership, not data ownership.
Correct.
Okay.
So really the takeaway point here, though, is that as the same logic, the same behavior we have today that grows us linearly from 7 to 15 blades, it's all done on a per blade basis. So as we push past 15 blades, we get that same behavior, that same logic, takes us all the way to 75.
Can you scale up the number of, I'll call them virtual storage controllers as you add more chassis and stuff like that? Because you wouldn't necessarily need that many for one chassis, but when you have 5 chassis, you need.
Right. So the question is the number of these partitions that you break the world into. Can you scale those out as you grow larger? So it's a really good question. What we've done actually since launch is we've increased the number of partitions that we configure into the system, and we also have a mechanism that will be coming later where you can actually take the control you can take the control associated with one of these partitions and actually split it into 2. Right. So we can actually change that number dynamically. All right, and so getting back to Ray's question from earlier, how do we make use of all the capacity within the system? How do we place data within the system? So if we take a look at data placement as we do it today within a single chassis, just taking a look at a chassis with 15 blades, as we place data, we place it into erasure code kind of RAID stripes, right? And so within a single chassis 15 blade configuration, we'll probably use about a 13 wide RAID stripe, right? So 11 data shards, 2 parity shards. The important thing is that we select these RAID stripes dynamically, right? We build them as needed. As we need to allocate flash, we'll select the optimal set of blades to use to place that data. There's no kind of static partitioning, no static pools, or any kind of static partitioning of blades ahead of time. Now, if we take a look at what happens as we add that 16th blade, well, nothing actually changes, right? From the point of view of kind of the logic that places data, we view the system again as just a large collection, and now a 16 blade collection of blades. As we need to place that data, as we need to allocate another RAID stripe, we just do that now with that 16th blade in mind.
Are you always using 11 plus 2, or is that variable as well, depending on how much data is being written?
Yeah, so it's a good question. Do we always use 11 plus 2? So smaller than 13 blades will obviously have to go down. At some point, which is right around 11 plus 2, we top out at that, and we keep using that forward. And really the reason for that is the kind of marginal gains that you get from going to wider and wider RAID stripes in terms of efficiency start diminishing quite rapidly. And so as we go and build out further to 17 blades, same thing kind of happens. We're, again, now dynamically selecting those blades to participate in that RAID stripe. And as far as making use of the data capacity, the kind of extra capacity of storage that you're adding with these blades, as we select these RAID stripes, right, as we're selecting the blades to place the flash on, we have knowledge of how much of this blade is being used and is available, and how much of the other blades are.
So there's no specific attempt to try to keep a stripe within a chassis.
So that's a very good question. So at this scale, right, when you've got a physical chassis with just 1 or 2 blades, you really can't, right, because you can't data protect there. Now, as you build out to, a larger configuration where you've actually filled up these subsequent chassis, it turns out that there are actually some benefits to constraining these RAID groups to live within that chassis, where it's feasible. And those benefits really come from the fact that if you can constrain if you can kind of bias the selection of these RAID stripes, these RAID groups to live within that chassis, what you can do is you can actually afford additional resiliency in the system. You can go from being able to survive, you can go from an N+2 over the entire system to more of an N+2 protection per chassis, right? So being able to survive not just two blades being removed from the entire system, but now 2 blades being removed from each chassis. Right? The additional benefit you get is that if you do have to do some sort of rebuild operation, right? Let's say you pull a blade and you have to rebuild this RAID stripe. Well, all of the data movement associated with rebuilding that RAID stripe, you can contain within that single chassis, right? And we can actually push the logic to do that rebuild into some of the compute units that are living within this chassis.
So today your minimum is a 7 chassis blade, and you go up to 15. Are you going to have similar types of limits for the additional chassis?
That's a good question. So today, our smallest configuration is 7 blades in the single chassis. We can go up to 15 in the single chassis. As we add additional chassis, there is no minimum addition, right? You can go 1 blade at a time, right? So we can go from that 15 blade chassis, and we can add a single additional blade. And what enables us to do that, again, is that all of the logic around control placement or on data placement really sees the system as just a collection of 16 blades. The fact that this extra blade is in a separate chassis form factor is just happenstance. It's just an artifact of needing to rack and stack it. Right? Cool. So we've talked about, we've talked a lot about how this works. But what's really, kind of really more exciting is taking this from architectural diagrams and seeing the, kind of frankly face-melting performance that comes out of this. And so, we're going to do a live demo, but they showed me a picture of this site, and I didn't know it was going to be such a high-tech warehouse. We were a little bit worried about what kind of networking connectivity we would have here. So we actually pre-recorded a bit of a demo from the engineering systems that we have in the labs late last week. I wanted to run you through this really quickly. And so what you're seeing here is, it actually works. Okay, so what you're seeing here is a capture of our GUI, if you haven't seen it before. In the upper left here, you've got a sort of a hardware health indicator. You can see we've got 5 chassis worth of blades, the fabric module port state, and now we've got additional hardware elements with the external fabric modules. We've got an overall kind of space storage capacity summary, but really the interesting parts here are the 3 moving graphs that you see. Right? So in the top graph, you've got latency, write latency in the red, and in the purple, the metadata. You've got IOPS, and you've got bandwidth. Right? And so this is running 100% write workload, and you can see we're pushing right around somewhere around 25, 30 gigabytes a second of write bandwidth sustained into the system, all to a shared namespace, all to a shared single file system over a single IP address. Switching the workload over to 100% reads, you can see the same thing here now with the reads. We're pulling, and this is with 3-to-1 compressible data, but we're pulling about 80 gigabytes, just peaked to 90, about 80 gigabytes a second of read bandwidth coming out of the system. And so this is really, proof point of that kind of linear build out and scale that we're talking about. If you kind of go back and do the math, this really does kind of divide back out to pretty much 5 times that single chassis bandwidth on both the read and the write side.
So Rob, a lot of the activity for standard file systems are all in metadata, directory lookups, things of that nature. How does the directory span across these structures, the blades, and that sort of? Is just more data as far as you're concerned?
Yeah, so as far as metadata operations, how we split the directories up, the biggest thing there is we don't have a single collection point for what's in the directory. It turns out that in terms of directory operations in a file system, the most common operation is looking up a file by name in that directory, and the most traditional choke point that traditional file systems have is they put all of that stuff in one place. We've actually spread that out and hashed it out so that as you're looking up a file by name, we hash that into a partition, right? So for that directory listing, that entire listing is actually spread and partitioned around. And so what we've got here, well, it kind of stopped running there, but this was now a mixed read and write workload. And you can see that we were pushing about 6 gigabytes a second of traffic into the system with writes, at the same time as pulling about 55 gigabytes a second out of the system.
With the latency graphs that you're generating, are you able to see tail latency or see percentile breakdowns of that? Because that's an average, which is pretty standard for people to have. Tail latency is the thing that generally kicks you in. Like there'll be 1 or 2 apps that happen to get really.
Right. So the question is about latencies and tail latencies, and do we display that? We don't put that in the GUI. It is available in the call home data. But what I'll say that we've learned with all of our customers' applications that are really pushing us on the performance end of things is that it's really the bandwidth that's driving those applications, right? We have a really tight tail latency to begin with, but what we see is that what's allowed us to really accelerate those applications is the bandwidth that we delivered. So, the numbers that Par showed earlier in terms of our kind of sequential growth and performance that's been able to accelerate their applications, it's really the bandwidth that's moved that needle. We haven't really done much on the latency front.
Okay, so for the FlashBlade, the kind of customers that you have are less worried about latencies. They just want to push lots and lots of data.
Yeah, that's a really good summary. The kinds of applications and workloads that we have are much, much more sensitive to pushing large amounts of bandwidth and throughput than they are about the latencies.
Remember, it still doesn't do snapshots, so you're not going to run OLTP on it anyway.
So I wanted you in it.
You can deal with that in other ones, but yeah, it's more kinds of apps that
Cool. So I'm getting the signal from the back of the room. I'm way over time. I just want to leave you with a couple takeaways here. The first takeaway is that it's really the software at the end of the day that creates scalability and parallelism within the system, right? Everything we talked about in terms of scaling that, performance and control placement and data placement, that's really all software, right? The hardware really exists to frankly connect things together. The hardware is just wires. That's what allows us to get at data, to get at the network, but it's the software that's creating that parallelism and scale. The second takeaway point is really just around how we view software and hardware integration within the platform. Our view on software and hardware development is, to take a very minimalist view towards hardware development. We want to do as little as possible there to create simplicity. What we want to do is we want to write the software to make use of the hardware we have in the most efficient way, right? And so that's what allows us to, for example, as we add that external fabric module, very easily move pieces of switching logic and software around in the system. But this philosophy also extends to how we manage and how we work with Flash, right? So we've developed kind of custom Flash controllers on the blades. We did that with the same philosophy, right? We did that primarily to create simplicity and density, but the way that we did that without tight coupling allows us to very rapidly move through NAND generations. And this is evidenced by the fact that the blades we're shipping today represent the 3rd and 4th generation of NAND chips that we've been working with, and we're working with the 5th and 6th generation NAND chips in the labs. We brought a bunch of them today. We'll hand them around during the break. But one of the blades that we're handing around, it was actually started out as a development prototype. We weren't planning on shipping it. It was really a stepping stone to accelerate development of a new NAND platform. And very quickly, the product team turned around and said, hey, there's a place for this to ship. Like, this would actually make a pretty good product. And we turned around and made that a production product. And I think it was like a month or two. It was actually a very, very quick process. And that really all comes down to the fact that we have a very, very fluid and agile system around our software-hardware integration. And the third takeaway point that I want to leave you with is, the simplicity in the system in terms of scaling beyond that first chassis in terms of network management really comes from the fact that it's software controlled, right? Being able to manage the network and everything around the storage platform as you scale to these kinds of configurations and sizes, it's a real challenge, right? And platforms and offerings that don't take control of that and don't simplify that and manage it internally, are really just kicking the can of complexity and management out to customers.